So assume that X is a compact Calabi-Yau n-manifold. So in general, it will be X and its mirror. No, what does mirror symmetry say about these two manifolds? Just to call some already. So there's sort of complex geometry of X, which I'll see as essentially the holomorphic volume form on X. So this determines a complex structure. So the holomorphic volume form is just so it's a holomorphic section of canonical bundle. And then there's also going to be a symplectic aspect of X, which will be given by the Kähler form. And these are interchanged when I go to the mirror. So we have the symplectic aspect of X, which we'll call the mirror Kähler form, and the complex aspect of X check, the mirror holomorphic volume form. And okay, they're interchanged. Now, usually we talk about, say, again, this is X check. That would be the, say, derived category of coherent sheaves on X, supposed to correspond to the derived Fourier category X check. And I won't really be interested in those so much today. I'll just be thinking about the simplest possible objects in each of them, which from my perspective are, for example, so the simple objects would be holomorphic vector bundles or Lagrangian submanifolds and, well, when I say Lagrangian submanifold, I should really include a little bit more information here. I'll allow myself a unitary line bundle with some connection, which I'll say more about later. Essentially, the reason I want to have this extra piece of information is because holomorphic vector bundles have complex moduli. Moduli of holomorphic vector bundles are generally given by some kind of complex manifold, and moduli of Lagrangian submanifolds usually real unless you add this extra piece of information which complexifies it. So it's some sort of formal trick, and however, will play an important role in the talk. And what's the main focus of the talk will be about, well, what you can say about holomorphic vector bundles or Lagrangians. One important thing we can discuss is whether, say, a holomorphic vector bundle is stable. So the corresponding notion by Lagrangian submanifolds is usually taken to be the special Lagrangian condition. So this means that if I take the holomorphic volume form, this big omega on X check, and well, in general, I might want to multiply it by just some complex scalar for normalization and restrict it to L. So this gives me a form on L. I want this form to be identically 0. So this theta here is just a real number. It's this phase of L. Now, my whole talk is going to be about trying to call this idea into question. So I'm putting quotation marks there. I just point out that at this point, well, I was careful to say that there's complex and symplectic aspects of x, and they get switched with the symplectic and complex aspects of x check, because already when we talk about stable vector bundles, it's important to choose a polarization of x. So the notion of stable depends on the Kähler form omega, which, if you're an algebraic geometer, you think of usually as the polarization. Of course, stability, in the sense of, say, Mumford, depends on polarization. So similarly here, too, although Lagrangian is a symplectic notion, the notion of stability, special Lagrangian, depends on the complex structure. Okay. Now, first of all, stability is an important notion, and I guess in the context of this conference, it's mostly coming from this when we talk about Donaldson-Thomas invariants. So right now they're known for, say, ideal shapes of curves, but in general one would like to define them for arbitrary stable objects in some kind of category of sheaves. And, well, by mirror symmetry, there should be some kind of counting stable Lagrangians in the mirror. The question is, what does stable Lagrangian mean? So let's do some examples. Well, there aren't very many. That's the trouble. So if we take x to be, say, the quintic threefold, or just say, just any, well, just for simplicity, a quintic threefold, so defined over R, well then, really the only special Lagrangians that I'm aware of, say, in the quintic threefold, are just, in the case it's real, you can take the real points. So it's a half-dimensional submanifold, which turns out the Lagrangian is also special Lagrangian. Okay, now, yes?
You also have some kind of Lagrangian sphere so that those are not special.
So there's definitely Lagrangian, but I don't know how to make them special. So they should be special, morally speaking, but I don't know if anyone has ever really shown how to prove that there actually exists a special Lagrangian representative of a vanishing sphere. So when you go to sort of compact, so there's many examples of special Lagrangians in, say, non-compact manifolds, but when you go to a compact, well, you also have some hyperkähler examples. If you go to, say, a compact three-dimensional calabi-Yau, which is not some kind of incarnation of a two-dimensional K3 or something like that, then it's very hard to cook up special Lagrangian submanifolds, as far as I know. There's various speculations about how one can do so, but I could even say this is unique. So, there's a lot of real structures in a quintic, and you can play around with it a lot, but it's a little bit too few for one's happiness. So the problems are, first of all, we're lacking examples. And second of all, well, stability usually has something to do with morphisms in whatever category we're talking about. So for example, if you're talking about stable vector bundles, stability is some kind of statement about subbundles. You need to know what an inclusion of a vector bundle is. In general, when you talk about stability in the sense of Bridgeland, so you have to know what an exact triangle is. So it's very unclear how the special Lagrangian condition relates to exact triangles in the Fukaya category. So one is something about complex structure. This is something about holomorphic. So I mean, these guys have something to do with, morphisms in the Fukaya category are essentially the floor cohomology, which has something to do with, so say J holomorphic curves, which is a purely symplectic type of thing. So, I should move the board up. So, to try and address these questions, I'm going to recall some, invariants of a vector bundle over X, and try to find the analogous notions for Lagrangian submanifold in X check. So first of all, there's just the Turin classes. So I mean, at this point, I'm really talking about some kind of C infinity complex vector bundle over X. There's Turin classes. Let me call it A. There's going to be sort of a hierarchy here, so of different invariants. There's Turin classes, and they essentially, you can say, Turin classes, which are just a class of some differential form, which depends on connection. So this would be some kind of connection on E. But the class, of course, doesn't depend on the connection. Then the next level in the hierarchy would be what's known as the holomorphic Chern-Simons functional. Which take geometers as so special integrated along with this is the secondary Chern class, known as a Chern-Simons class. And sort of the reason this is considered to be secondary is because this exactly measures the dependence of the Chern class on the choice of connection. So the Turing class doesn't depend on the connection, but its representing form does. So if you take the exterior derivative of this differential form, it's going to give you exactly the Turing waveform of d1 minus the Turing waveform of d0. And, well, this is an outline of a definition. But what's more interesting is the properties of the of this functional. So first of all, let's suppose that d1 is a critical point of the functional L of d0 and just an arbitrary connection. Well, this implies that actually, so up till now we were considering just a C infinity complex vector bundle. But now if d1 is a critical point, then d1 defines a holomorphic structure on E. So it's integrable. Well, I should say the 0, 1 part. So being critical for holomorphic Chern-Simons functional is exactly equivalent to defining a holomorphic structure on the vector bundle. So another interesting property of this functional is that L is invariant under gauge isotopy. So what does that mean? So if I have a family of C infinity automorphisms of my vector bundle E, say where T belongs to the interval 0, 1, and let's say G of 0 is just the identity. So then gauge isotopy would just mean to change d1 to just a pullback by this gauge transformation of itself. That's a gauge isotopy. So one can see that the holomorphic Chern-Simons functional is invariant under this sort of gauge isotopy. And just as the Chern class is kind of defined as the class represented by some form, but it doesn't depend on the connection, so too, well, the Chern-Simons functional, it's got to do with integral of some form, and it doesn't depend when the connection is changed by a gauge isotopy. So when you have something which is independent, you try to define a secondary invariant. So as soon as you see this invariant, so that means you want to define another secondary invariant. Sorry. And that secondary invariant will be what's known as the Donaldson functional, which is extremely important in studying stability of a vector bundle. So the Donaldson function I'll denote M of D and a gauge isotopy. Okay, so it's going to be, so first of all, it's defined only for d which are critical for the Chern-Simons functional, defined when d01 is integrable. So this is a critical point of holomorphic Chern-Simons. And then we'll measure kind of the independence of L on the gauge isotopy. So it's going to be the integral of another differential form. This is just as this was some kind of, I should have said this is differential form. And this will be another differential form. Which will now say exactly how t changes. So, or how the change is exact. And now I'm going to replace the holomorphic volume form. Since we're talking about stability, it will have to be replaced with the Kähler form. So this will be, just put in the exponential of the Kähler form. So, which just means you put in the right power of the Kähler form, which can be integrated against this. This is called a Bott-Chern class. Actually studied by Bott and Chern in the 60s. So now the defining property essentially of R is that if you take del of R, this will be the same thing as, so del of R, d and gt. This will just be the same thing as the, so this is the, this is the 1,0 part of the d operator. So this will be just t of d and g1. So you know that the Chern-Simons class, when you evaluate it on some kind of gauge isotopy, is going to give you something which is 0, essentially, when you integrate it. And the reason is because it's just given by del of the Bott-Chern class. And in fact, you can see that del bar of this guy is actually equal to the change in the Chern form. This is the more standard formulation of the Bott-Chern class. So now why is one interested in the Donaldson functional? This is essentially introduced by Donaldson in his thesis, which was devoted to the Kobayashi-Hitchin conjecture. So essentially, m of d and something is bounded below if and only if the holomorphic vector bundle defined by E and the 0, 1 part of this connection is stable in the sense of Mumford. Well, assuming you, I mean, there's different kinds of Bott-Chern classes. One has to. Sorry? Yes.
So, yeah. So in your definition of this Bott-Chern class,
yes.
Is that only depending on the G1, or I mean, seems to me the definition only depends.
So
it shows a different isotope, gauge isotopy, and so when d is less than 1, they're not equal. Would that be the same class?
okay, so I'm about to say something about this. So first of all, when I say this, I should really talk about D and GT metric in some sense. So there's some question of the functional being real, which depends on some kind of metric. But that's sort of a secondary point here. And second of all, which is just the question, well, m d gt depends only, well, it's invariant under homotopy of gt relative to the endpoints of the interval 0, 1. Okay, so I think I'm just going to reuse this word because otherwise I just will be hidden. Okay, so right, so again, addressing the question, if we consider connections and isotopies coming from families of metrics, then, well, the space of metrics is contractible. So then we get something which only depends on the endpoints. However, the space of gauge transformations is not necessarily contractible, so I have to be careful and just say that it's a homotopy invariant of the gauge isotopy. The reason I'm phrasing things a slightly non-standard way is because when I look at the mirror picture, then the meaning of a metric won't be quite clear. So what's the mirror analog? Of course, if we can somehow convincingly mirror this functional m, then we'll know what stability for Lagrangian submanifolds is, because, well, m is bounded below even if and only if the Lagrangian is stable. So start again with the same sequence of invariants. There's A. So this would be something essentially analogous to the Chern character. So if we have, well, by the way, I'm going to start now L contained in X. So before I had to start, in order to see all the different invariants in their kind of full glory, one had to start with just C infinity vector bundle. So the analog of C infinity vector bundle would be to look at a submanifold which is not necessarily Lagrangian, but say totally real. This just means that if I take the tangent space to L at a point, so then it's transverse to the complex structure I acting on the same tangent space. There are subspaces, of course, of the tangent space to X check at that same point in L. So this is just a parenthetical. This is totally real. This is kind of sort of a relaxation of the condition of being a Lagrangian. Just like being a complex vector bundle, which is just C infinity, is a relaxation of being holomorphic. So the Chern character is widely believed to be just the homology class of Lagrangian, the fundamental class of Lagrangian sitting inside of X check, at least the first order approximation. Okay. The holomorphic Chern-Simons functional, its mirror has been studied extensively starting with Witten over around 15 years ago. So even more. So the the mirror turns out to be something like the classical Chern-Simons functional. So the real Chern-Simons functional with what usually called instanton corrections. Okay. For the enumeratively minded among you, this sounds like a very physical type of a thing, which maybe not have any particularly clear mathematical interpretation, but one can actually look at the critical points. This is, started by Witten, but later on, it was shown actually mathematically that if one compares the critical values of the Chern-Simons functional with the instanton corrections with the critical values of the holomorphic Chern-Simons functional, one can actually deduce enumerative equivalences. So there's a paper of Pandhari Pandey, myself, and Walcher, where we actually compute a critical value of this mirror holomorphic Chern-Simons, and it turns out to be disk enumeration. So on the quintic threefold. So this is, so I would say mirror symmetry at this level of the Chern-Simons function is very precisely understood. So you can actually prove a open mirror theorem. So I'm going to denote this functional as L check of L0, D0. So D0, again, is this connection on this line bundle over L0. And without going into the details yet, just its properties are almost exactly those of the holomorphic Chern-Simons functional. So the critical points, for example, of this real Chern-Simons plus instanton corrections, which are known as L check. So if, let's say, L1 D1 is a critical point of L check L0 D0 something, so this means that, in fact, L1 is not just totally real, but it's actually Lagrangian. And moreover, in a way that I'm going to explain in a few minutes, D1, it gives rise to what's known by Fukaya, Oto, and Ono, a bounding form for the A-infinity algebra associated to L1. So D1, okay, that was a mouthful. It's going to be just a picture in just a second, so don't mind what that means. So D1 is, so it leads to a bounding form for A-infinity algebra of L1. So this is in the sense of yes, so I'm going to write that in just a second. So L check is really, in a sense, the superpotential. But it's a little bit more well-defined than the superpotential. So I mean, if we really want to make sense of the superpotential, you should really think of it as being some kind of relative invariant between two Lagrangians, and so on and so forth. So a domain wall tension or something like that. There's got to be two branes involved. Sorry? Yeah, so one can express the holomorphic Chern-Simons functional as just an integral over some chain bounding the difference of two algebraic Chern classes. That's how we, well, I guess the B side of this was done by Walcher and Morrison, so maybe we should add that as well. So they really compute some integral over a chain which bounds difference of, okay, so I mean, what's the point of a bounding form? Essentially, a bounding form is necessary in order to define HF, the floor cohomology of L of anything and L1 D1, floor cohomology. So often in talks on floor cohomology, people don't mention the bounding chain because they're working in, say, for example, the case when all the Lagrangians are exact and the bounding chain is just 0. And there's other cases in which bounding chains vanish. But in general, one needs to define, in order to define floor cohomology, you have to have this bounding form, bounding chain. So you can think of it as when you try to define the Hom between two, say, vector bundles, in the sense of, say, think of the vector bundles as coherent sheaves. And to define the Hom between them, of course, you need to know what the holomorphic structure is on them in order to define Hom. So just like you need there's just holomorphic sections of this Hom bundle. So another important point here is, of course, that, again, the functional is invariant it's invariant under the appropriate notion. Well, instead of gauge isotopy, just taking a gauge transformation of the bundle and applying it to the connection, the right thing to do here is to take a Hamiltonian isotopy of L1, let's say. I mean, it could be either one. Of course, it's symmetric, the definition. So, and then the question is, what do you do with the connection over there? And, well, I'll try to draw it in a picture, but algebraically speaking, it's going to be just apply an A infinity homomorphism of, well, whenever I have a Hamiltonian isotopy, it actually defines an A infinity homomorphism. So you take the A infinity homomorphism of this Hamiltonian isotopy, which connects the A infinity algebra of L1 and its image under the Hamiltonian isotopy, and you apply it, in some sense, to D1. So this is something which involves, again, counting holomorphic disks. So I'm going to draw it all in a second. So So I mean, this two things together correspond to gauge isotopy. This is the mirror of gauge isotopy. So as soon as you find something which is invariant, as usual, you do secondary invariant. So you have a primary invariant, which is the Chern-Simons functional with instanton corrections, and it's invariant in some gauge isotopy. It means that you expect somehow this invariant to be exact in some sense, and you will look for a form which makes it, you look for some kind of chain which bounds it, and that chain itself you expect to be a secondary invariant. So the question is, how do we do that? So we want M check should be the secondary invariant measuring the exactness of B. I guess I should have called it A check and B check and C check or something like that. Worse. A check, B check, and C check, B check. We want to measure the exactness of B check under mirror gauge isotopy. Okay. Well, to do that convincingly, I want to actually tell you what the Chern-Simons functional with instanton corrections looks like, and a little bit about its critical points. So, of course, this will only be defined on L1D1, which are critical points for L check. Okay, so just like the Donaldson function was only defined for critical points of the holomorphic Chern-Simons functional. Okay, so first of all, I have to say a little bit more about this connection, which I've been talking about on the line bundle, D1. So more about L1, well, LD. So this is as I say, D is a connection on a unitary line bundle. L goes to L. So the thing is that this connection cannot just be a regular connection, because there has to be some kind of dependence on the Kähler parameter. So the easy way to do this is to say that D is some D0, which will actually be a unitary connection in the usual sense. Unitary connection. Okay, plus, well, in general, when you define a connection, so what we really want to say is that D is a connection with coefficients in Novikov ring or something like that. But it's sort of hard to say what coefficients in a Novikov ring are for a connection. But the thing is that any connection, you add a form to it, you get another connection. So I can start with a regular connection and add just a one form. And this defines a new connection. So B will just be a one form on L with coefficients in a certain lambda plus, which is a sort of a Novikov module. So for the purposes of this talk, and I mean, just to save time, I'm not going to say the whole definition because it's really trivial. I'm really going to think of lambda plus as roughly speaking, be C adjoin some formal variable, but I allow sort of real powers of this formal variable for positive exponent, positive real exponent of a, okay, you have to put some kind of condition on the exponent so that the thing is complete, but that's just a pain. Okay, so that's really what I want you to know about D1. It's just a regular connection plus some 1 form, which has got coefficients of the Novikov ring. And then it's possible to write down this. So L hat of the thing we're interested in is, so just for simplicity, I'm going to assume that the dimension is 3, because then the holomorphic disks become discrete, and there's just a finite number at any given homology class, and so it's easier to sum over them. Things will become easier to write. So the holomorphic, the mirror holomorphic Chern-Simons function, or L check, is given by some classical part, which I won't be interested in. That sort of assures that L is Lagrangian when you look at a critical point. Plus, then there'll be something which counts holomorphic disks with boundary on L. That's how we got to enumerating disks on the quintic threefold. So it will be essentially U, which takes disk to X and L1. It'll be holomorphic. It'll be a sum over all the disks which have which take the disk to X and its boundary to L1. This is an elliptic boundary value problem. And we want to weight, so we sum the weight for each disk is given by, well, plus minus the holonomy of the connection D1. You can make sense of a holonomy of a connection with Novikov ring coefficients, and you want to take its holonomy around the boundary of the disk. So U restricted to the boundary of the disk. And then you, in addition, multiply that by the formal variable to the power omega of D. The Kähler class, I should say omega check, of omega check of, let's say this, integral omega over, yes?
Do you have any thinking on Maslov index?
Okay, so, oh, you're right. I should have said that yeah, all Lagrangians have Maslov class 0. Okay, sorry, Youngman. So from the beginning of the talk, I should have been talking about all, I mean, throughout the whole talk, everything I said would have made sense essentially only for Lagrangians which have Maslov class 0. Thanks. And then I just do minus the same thing, but now I take the target being L0, and then, yeah. And then again, I have the holonomy of D0, the same thing. Okay, and then, of course, I have to add some extra terms which won't be important for this discussion, which have to do with holomorphic spheres. Okay. Now, I said that a critical point of this L check is, it says that D1 somehow gives you a bounding chain of L1. So how does that actually So I'm going to leave that on the board. So I want to explain that how does this happen, that D1 actually gives rise to a bounding form. So of course, the bounding form is going to be B1, okay, which I've just explained how D is a sum of sort of D, I should have said 0 up there. So DI is a sum of D0I plus some form BI. And, well, one can expand this thing is equal to, so the sum over k equals 0 to infinity of, so just the first line will just be the sum over k equals 0 to infinity of the A infinity operation applied to k times b, paired with b, and integrated over L. So don't pay too close attention to this, because it'll soon be turned into pictures. OK, so this implies that if you vary, so I start divide by k plus 1. So this implies that if you take the variation of, so this is just you expand the time-ordered product. So Taylor expansion, essentially. And the result is, well, a critical point. If you just take the derivative of this thing, think of it as being a polynomial, a monomial in b. So you take b to the k plus 1 power, you take the derivative, you get just b to the k power. So then critical point equation is just that the sum like that is equal to 0, which is exactly the Morra-Cartan equation, which is what a bounding form has to satisfy. OK. Now, the question is, what does this mean geometrically?
What are these?
So the B is, sorry, B1. OK? And the MK takes into account the unitary line bundle, the unitary connection D0. So this depends on D0. OK, this just takes the monodromy into account. So I'm just going to draw for you what it means to be a bounding form at degree, so at lowest degree. OK, picture of a bounding form and for simplicity, I'm going to ignore all disks which don't have minimal energy. So only draw holomorphic disks of minimal energy. So these are some A infinity operations. So I forgot to say, yeah, the A infinity. So MK just maps forms on L, tensor K to forms on L, the A infinity algebra structure. So the picture of a bounding form is just that, so in particular, these MK, they include lots of holomorphic disks. So a bounding form looks like this. Essentially, there's going to be a bunch of disks ending on L. And I'm not going to draw them all, because it could be a very lot. And a bounding form will essentially be just what you think it is. It bounds the boundary of the disk. So again, I'm thinking here, for simplicity, of the case, so So this is going to be a picture of the Poincare dual. Poincare dual of B. So I'm just label it B. So B is a 1 form, so its Poincare dual should be a sort of a surface. A surface in L, which is just a 3 manifold. And the boundary of the surface will just agree with the boundary of holomorphic disks with boundary on. So this is going to be a picture of, this is going to be U from D to XL. Okay, this is a bounding form. Okay. Next step, this is only pictures from now on, which will take a few minutes, just 2 or 3 minutes. They're a little bit late. So a bounding form just bounds the boundaries of the disks. So the question is, well, if we want to find some way to measure the exactness of L check, we want to write L check as the integral over X check of some T check. Wedge, of course, I'm going to switch capital omega with little omega. And we want to find out what a picture of this T check is. So the picture is just like that. So I'm going to assume now that L0 and L1 are Hamiltonian isotopic. So assume that phi t Hamiltonian isotopy. Lt is equal to just phi t of L0. And of course, so then there's going to be, of course, in between, there's going to be some kind of Lt here. Okay, now there's going to be my disks. And again, I'm just drawing disks of minimal energy and only considering all contributions of minimal energy. So, okay, actually, remember, as you move L along, the disks can move around in very complicated ways because you're taking some kind of pretty nonlinear problem. So, I mean, the disk can start to twist around in all kinds of interesting ways. Maybe I should get over there. Okay, and it turns out that, I mean, it's pretty easy to convince oneself just by thinking about the picture that T check should just be a chain which looks kind of like this. Should just be kind of the path traced out under the isotopy by the boundaries of the holomorphic disks ending on the Lagrangian. So this is again some kind of surface because it's sort of a family of boundaries of disks. So this is T.
The bubble, right?
Sorry?
In a one parameter family, you can get the disk bubble.
Yeah, I'm only drawing disks of minimal energy.
Okay.
The whole point of this is that, I mean, this would be trivial if there weren't bubbles. So everything I'm doing here is really interesting geometrically because there's huge bubbles and all kinds of stuff which is going on here. And but since it's minimal energy, that doesn't happen. So, but just to give the basic geometric idea. So again, T check is going to be some, it's going to be a surface, right? Which is a Poincare dual. Now, the question is, what is going to be the R check, which bounds this surface T check? So well, the boundary in two different senses. Of course, we should just take the family. I mean, it's clear if you look at this picture and then you look at this picture, how can we fill in this surface here? Well, we should take, of course, it should be something like the del derivative as opposed to actual boundary. So I'm going to take only the boundary kind of one direction. And, well, it should just be essentially the, okay, this is a bad drawing. Should be the family of BT, which fill in they're the bounding chains for each LT. Okay, and the family altogether will make a three-dimensional chain. Okay, so you have a bunch of surfaces. So this is going to be, so the union over T of BT, which is going to be essentially a three-dimensional chain, a Poincare dual. And once you have a three-dimensional chain, of course, you can just integrate. So then M will be the integral over this chain T check, R check, excuse me. It's now a three-dimensional chain. You can integrate over the holomorphic volume form. So it's better to consider the imaginary part. It's kind of exactness here. And this is going to be the definition of the M check. And the theorem is that doesn't depend on homotopy. Theorem, M check, invariant under homotopy rel 0, 1. Now this sounds like, well, you have some kind of thing. When you vary it, it should be, well, this is not so simple because you're taking some kind of chain which has boundary and you're moving it around. So when you move a chain with boundary, the integral of some form over it can easily change. So the proof is essentially the fact that you can fill in the boundary of this chain, R check, with holomorphic disks. What does that help you? The integral of a holomorphic form over holomorphic disks is always 0. So integral of im omega over, well, a chain which is filtered, which is foliated by holomorphic disks is equal to 0. So filling it in doesn't make a difference. And of course, the last thing is just that when you look at the example of something which is the real points, then you necessarily get xr. If you take L xr, then a paper of these guys implies that you can take B trivial, which implies that L1 is critical point for M check. So in particular, the known examples of special Lagrangians are all critical points of this new functional. So that's where it'll end.